Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to a concept called gravitational acceleration. So let me talk about what we're looking at here. We've got this young lad here, Timmy. I use Timmy for a lot of my examples here. And imagine that Timmy's standing at the top of this building. And we're going to talk about what happens when Timmy drops this basketball. Now for the sake of example here, we're talking about things like a basketball or a rock or maybe his keys or something, things that are relatively large, heavy compared to their surface area. We're not talking about things like tissue paper or a beach ball or things like that. Because with a tissue paper or a beach ball, air drag is a very significant factor. If Timmy drops this basketball, air drag is not going to be a significant factor, at least for a little while, not until the ball picks up quite a bit of speed. All right, so when Timmy drops the ball, if I were to draw a motion diagram for it, and just a reminder about a motion diagram, basically that's like a digital camera taking snapshots in time. Click, 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 and imagine superimposing the pictures. So I'm going to use a dot to represent the ball. It's going to start out here. And when the ball's moving early in the trip, like when Timmy first drops the ball, it's not really moving very fast yet, so it doesn't cover a lot of distance in that first half second or so. But as time goes on and the ball speeds up, it starts covering more and more distance. Right? So the motion diagram might look something like this. I might put velocity vectors in here to represent the speed and direction the ball is moving in. So that first vector, might point something like this. These vectors point downward because the ball's velocity vector is downward. The ball's moving down. And another important thing to realize is that these vectors would be increasing in length because the ball's moving faster and faster and faster. Right. Now, velocity is a vector quantity. So whenever you deal with vector quantities, you always want to define a coordinate system to talk about directions. I'm going to go ahead and put a coordinate system right here. I'll put it in green. So let's say here's my y-axis. Oops. Here's my x-axis. Now, you can orient a coordinate system any way you want. I'm just orienting it like this because most coordinates that you've ever seen, or most coordinate systems that you've ever seen, probably had this type of orientation. Now, the ball's motion is one-dimensional. It's moving basically up and down, or in this example, just down along the y-axis. So we would track the location of the ball with a y-coordinate. I've got the positive y-axis pointed up. The ball's velocity is down, and the way we would take that into account is with a minus sign when we describe the velocity of the ball, at least graphically. What I'm going to draw over here now is a graph of what velocity against time for this falling ball might look like. So if Timmy dropped the ball at t equals 0, the velocity of the ball would be 0. Right at the instant he let it go, it's not really moving yet. So the first point on this graph over here on the right would go right here. And again, I'm going to graph velocity against time. Now, as a little time goes by, the velocity of the ball is increasing in a negative sense. Like the velocity here might be something like, minus 1 meter per second. And then a little time later, it might be minus 2 meter per second. A little time later, maybe minus 3 meter per second, and so forth. So this graph might look something like this. 1 delta t goes by. The velocity would be some negative number. Now, what that number is, not important for the discussion. Now, why would it be negative? Well, the velocity vectors point down. And in this discussion, I've defined up as positive. And then another delta t goes by, and the velocity is going to change to some new value. Again, what the number is not important quite yet. And then another delta t goes by, and the velocity is going to change by another increment. So this graph is going to look something like this. Now, I'm going to call this case 1. Where the ball is dropped from rest. Let's imagine here another case where Timmy takes this ball, but instead of dropping it, maybe he throws it up in the air first so that the ball travels a path maybe something like this. And I'm going to call that case 2. So the ball's moving in this direction, something like this. Now, For case 2, at t equals 0, the velocity of the ball is pointing upward if Timmy launches that ball upward. So since I've defined up as positive, this would be some positive number. So if I were to graph that over here, at t equals 0, the velocity is some positive value. I'm going to go ahead and give that value a name. I'm going to call it v sub o, standing for the initial velocity of the ball. Now, important thing to realize is as the ball is on its way up, it's moving slower and slower and slower. And at the top of the arc, as far as this one-dimensional motion is concerned, its velocity is actually 0. So this graph, right, as the ball is moving upward and time is moving on, the velocity is dropping. And there is actually some time where that velocity is 0. That would be when the ball's at the highest point of the arc. So this graph might look something like this. Now, after this point in the curve, the ball starts moving downward. And at that point, the velocity vector of the ball is pointing downward and increasing in a negative sense, kind of like it was before. So on my graph here, that means the velocity is going to be some negative number, because when the velocity points down, that's in the opposite direction of the direction I've called positive. So this graph kind of continues on, maybe something like this. Now you'll notice I've drawn these with similar slope, and it's pretty easy to show that as long as that ball or rock or key or whatever it is fairly heavy compared to its surface area, these two cases would have the same slope. And that slope is the rate that the velocity is changing And if you see my previous videos about acceleration and rate that your velocity is changing, right, that's what acceleration is, rate that your velocity is changing. If you were to actually put a motion detector and measure the acceleration of this ball, you'd get the same value on both of these curves. And that value is called the free fall acceleration. It's usually denoted with the letter G. And that value is about 32 foot per second, or in metric units, about 9.8 meter per second. Right? And that's what's referred to as the free fall acceleration. Most objects at the surface of the Earth, and when I say most, I mean this, any object that's at the surface of the Earth that's relatively large compared to its surface area, so like a rock or a bowling ball or things of this nature, if you drop them or you throw them in the air, or if you throw them downward for that matter, they will experience an acceleration approximately equal to 32 foot per second, or about 9.8 meter per second. Lighter objects, like maybe something like a beach ball, won't experience an acceleration like this, because for a beach ball, air drag is a much larger or a much more important force at low speeds. So a beach ball's acceleration when you drop it probably isn't going to be 32 foot per second. It's going to be something significantly less. If we were to somehow put this in a vacuum, remove all the air from it, and I were to drop a beach ball, maybe a feather, humor me, that's supposed to be a feather, and a rock, if they're all in vacuum here and air drag is not a factor, each one of these will accelerate down and hit the ground at pretty much exactly the same time. And the acceleration of each one of these would be about this value, 32 foot per second. So I made this video just intended to be an introduction into gravitational acceleration. I'm not going to talk about any math or look at any problems right now. Just the idea is this, that in the case of a vacuum at the surface of the Earth, all objects will accelerate down at about the same rate, 32 foot per second. When you include air drag, and that's a pretty important case, because typically we live in an air pressurized environment here, the free fall acceleration of a relatively heavy object like a rock or a bowling ball or something will still be pretty much 32 foot per second. But something light like a feather or a beach ball, that won't be true anymore, because air drag will be too significant of a force. So anyway, again, this video is just meant to be an introduction into gravitational acceleration. I hope that that's successfully done that for you. Have a great day.